Alright, so in the previous video, we said we are going to discuss question number 2. Question 2, an important question anyway. There are many questions that can be answered, but these are the top ones that usually come up, right? Important variables. Which ones are important, right? Important variables. So now, in the previous video, we said the first step is to compute the F statistic and to estimate the associate p-value. When you have the associate p-value, you now decide, is there a relationship between y and the axis? If you say yes, there's a relationship between y and the x-axis, in this video we're going to say which axes are important, right? So what we can do is we can look at the individual p-values as long as p is not too large, right? So here, if we've, let's say 10 predictors, right? TV, newspaper, billboards, flyers, whatever it is for ourselves, we can look at the individual p-values themselves. So that is one approach. P-values, if p is not too large. So these p's are different. This p means the number of predictors, right? And this is the statistical p-values, the probability values and stuff like that, right? So if p is not too large, we can look at the p-values and get parameters and get the predictors that have very low p-values. Those are the ones that are important, right? Those are the ones that are significant. But now imagine if in some cases when you are really doing data science, you might get into situations where p can get all the way up to like 10,000 predictors. So you have 10,000 predictors, beta 1, beta 2, beta 3, all the way up to, like, imagine beta 10,000 or beta 1 million, right? It's possible to get to beta 1 million. So what would you do in that case? There's no way you can look at each individual p-value and be like, oh yeah, this one's significant, this one's significant. 10,000 p-values, you cannot do that, right? So you might think of a second situation. So a second situation might be all the p-values, maybe they are not all significant. And in that case, it means your y is associated or is a relationship with only a subset. It's only related with only a subset of all the predictors, right? Subset of all the predictors. So selecting these variables, it is called variable selection. Selecting which ones they are, which ones are important, right? So one could perform variable selection by trying out a lot of different models, each containing a different subset of the predictors, right? Let's give a simple example. What we mean is, let's start with p equal to 2. P equal to 2. So one might say, okay, I'm not going to use this normal method of looking at the p-values. What I'm going to do is, I want to choose the model that has the best subset, right? That's what you're saying here. You know that there is a model with some of these b's here, some of the predictors, but not all of them. But it could be all of them. But you want to choose the model. Maybe it's the best model is the one which has beta 1 and beta 2, or beta 2 and beta 3, or from beta 3 all the way up to 10,000. Maybe that's the best model. So that those are subsets of all the p's. So here, let's say we have p equal to 2. What subsets can we make here? We can make model number 1, called the null model. And this null model will have no variables at all. There's no variables. It will just have the intercept, beta naught. That's all. Okay. Model number 2, it will have only model with x1 only. Right? So it will be something like y is equal to beta naught plus beta 1x. Right? And then a third model could be x2 only. So it will be y is equal to beta naught plus beta 2 x2. So this is x1 here, x2. And then we have a fourth model. x1 and x2 both, right? So it will be y is equal to beta naught plus beta 1 x1 plus beta 2 x2. So these are the 4 models that we can make from taking subsets of p equal to 2 when we have 2 predictors. When you have 2 predictors, you come up with 4 models, right? So one will fit this model and fit this second model, third model, fourth model, and then compare the results of these and choose the one that performs well. That is one approach. But this works with this what? So when I'm saying choose the model that is the best results, there are many ways, and we are going to discuss them later when we do model selection. I think it's a later chapter, but you can use models like Mallows CP, archaic information criterion AIC. You are going to see all of these later. Or you can use Bayesian information criterion, which is called BIC, or adjusted R squared. Right? Many people love adjusted R squared because that is where many people start off. We start off learning adjusted R squared, choosing the best model amongst models using this thing called adjusted R squared. But these are very, very powerful ones, and we are going to see them later when we get to that variable selection chapter. Cool. So now that you have chosen your model, you're happy. You'll be like, oh yeah, maybe it's model number 3 that gives you the best result, or the highest adjusted R squared. All right, cool, right? But this worked when p was equal to 2, right? P equal to 2 gave us 4 models to compare. Now imagine if p is equal to 30. Imagine how many subsets of 30 we can make here. The now model, the model that is x1 only, x2 only, x3 only, x4 only, up to x30 only, model that is x1 and x2, model that is x1 and x3, model that is x1. There are so many models that we can make doing those subsets. There are so many models. Actually, there are 1,073,741,824 models that you can make when you have just 30 variables. And I'm saying in real life, 30 variables they're usually nothing. When it comes to data science, 30 variables are nothing, but they are leading to these models. Imagine trying to come up with these models and having to compare them and choosing the best one. That's a lot of work. That is a lot of work, right? It is pretty much not practical to do 1 billion models, right? So unless p is very small, we can't consider all, and this is calculated by 2 to the power of p. Anyway, the number of models you'd have to consider using subset, it's calculated by 2 to the power of p. When p was 2, we have 4 because it's 2 to the power of 2. When p is equal to 30, we have 2 to the power of 30, and this is the answer here, right? So we need an automated and efficient approach to choose a smaller set of models to consider. So before we even get to all this billion, can we drill it down to a smaller subset? That's what we are discussing in this video, right? So there are 2 ways of doing that. You can do what is called forward selection. Do forward selection, right? So what forward selection does is, step number 1, begin with the null model. Begin with null model. So it's y is equal to beta naught, right? That's all you have. And then step number 2, so what you're going to do is you're going to fit p simple linear regressions, right? You're going to take each variable. You'll be like, for x1, so fit p, and these are simple linear regression models. Linear regression models, right? So what this step does is, let's say we have 3 or p is equal to 5. We're going to fit 5 simple linear models, each separate. So it's going to be, the first one is going to be y is equal to beta naught plus beta 1 with the first parameter, right, or predictor. And then the second one is going to be y is equal to beta naught plus beta, whatever beta is going to be, but with the second one. And then you're going to do y is equal to beta naught plus beta 2 plus beta 3 x3, all the way up to when you get to x5. So these are separate simple linear models. And then after you do that, what you then do is you will choose the one. So you in this case you're going to say, because you now calculate what is the RSS for this, what is the RSS for this, what is the RSS for this. Then if the lowest RSS is coming from like the model that is x2, you take x2 and you add it to our null model. So you then now add lowest RSS predictor to null model, right? So now you have y is equal to beta naught plus the one that was beta 2, but it's actually, you can now, this is the overall model, so it's now like something like this, right? Beta 1, not the same beta 1 here, no, it's just a beta 1 there, just random beta 1. And now we've added our x2 to our, because that's the one that gave us the lowest RSS when we're doing this, when we were doing the simple linear models, right? So this is now our new, this was our first model, this is now our updated model. Cool, right? And then, well, after you do that, you then fit again, you then add again. Remember these ones here. You sort of so now we know what this is. We now know that this is now like a one-dimensional, because we just have one dimension here, right? So we then add to that model the variable that results in the lowest RSS for the new two variable model, because here we're going to say, okay, now we have added the lowest RSS is going to be x2. Which one is the second lowest RSS? Maybe it was x3. We add x3. Or what we can do actually is, without adding x3, this is now our model, right? x2 is gone. x2 is gone. We have x4 and x5 left. What we are going to do is take this new model and then we put x1. Let's add x1. We're going to add x1 and we calculate the RSS. And we're going to say, okay, when we added x1, this was RSS. We add x2, we add x3, I mean, x2 is already there. We say, oh, when we added x1, this was the RSS. If we added x3, this was going to be the RSS. If we added x4, this was going to be the RSS. If we added x5, this was going to be the RSS. You get what I mean? So it will be x2 plus either x1 or plus x3 or plus x4 or plus x5, right? Isn't? And then here we're going to say, okay, which one results in the lowest RSS when we've added it? It will say maybe x1 results in the lowest RSS. Cool. We keep at 1. So which means now our model is something like this. x1 done. And then we start the process again. What happens if we add x3? What happens if we add x4? What happens if we add x5? Then we choose the one that will lead to a low RSS. Is it x4 that led to a low RSS? Cool, we update our model. Beta naught plus beta 1 x2 plus beta 2 x1 plus beta 3 x4. Now we're left with what? Adding x3 and then we add x5 I mean. And we compare the RSS. So going like that, that's why it's called what? Forward selection, because we are building it as we go. We are building it as we go. Until maybe some stopping rule is satisfied. Because here we might say, this one here, adding x3 and or adding x3, x5 I mean, it has led to just a big jump in RSS. These two are completely useless. Let's stop here. The RSS that they are now adding is now way too much. So let's stop here. This becomes our model, right? That becomes our model. This works, but also it is a problem of dimensionality, because imagine we had 30 of them. It will be much faster, of course, than doing this 1 billion. Definitely it will be much faster, but it will still have those issues, because at each stage we'll probably at most we'll do 30 models, at most 30 models, which is much faster. But it would suck to just add and compare. It's not going to be at most 30 actually. It's going to be it's going to be more than 30. It's going to be more than 30, because at each step you are running the models again at each step. So yeah, when you did first step, you ran 4 models. Second step, you ran 3 models. Fourth step, you ran 2 models. Fifth step, you probably run 1 model and stuff like that. So when you add up those, it's not going to be 30, it's going to be more than 30, right? But the number is definitely going to be less than this 1 billion, definitely, right? So that is forward selection. Let's quickly talk about backward selection. So another method could be backward selection. We'll just quickly go through this backward selection. So backward selection is you start with all variables in the model, right? All the variables in the model, you fit them, and then you remove the variable with the largest p-value. So yeah, start with all models, with all predictors. Start with the model with all predictors, and remove one with largest p-value. Largest p-value, right? Because that one is the most useless, I would say. Is the most useless. So now you'll be left with a model that is p minus 1 variables, right? Fit that model, and then remove the one that is the largest p-value again. So now you're left with p minus 2. Fit that model and remove the one with the largest p-value again, right? Going and going and going like that until you reach a stopping criteria. So your stopping criteria might say, okay, when my p-values are now in this range, I'm stopping with however many variables I have left when I have reached that clean p-value. So that is backward selection, because you are selecting going backwards. You start with all predictors and you remove, right? So now the third one, as I'd say 2, but then the third one is not really a method on its own, but it's called mixed selection. It's called mixed selection because you'll be mixing forward. It is forward plus backward selection. Forward plus backward selection. So you start with no variables, as with forward selection, and add variable that provides the best fit, or that provides the lowest RSS, just like forward selection, right? And then you continue to add variables one by one. Now, p-values, you'll be monitoring the p-values. The p-values can become larger as new predictors are added to the model. Hence, if at any point the p-value for one of the variables in the model rises above a certain threshold, then you remove that variable. So you keep adding, monitoring the p-values. If one of them goes above a certain level, you remove that one. Doing backward selection. That's why it's mixed, forward and backward. And you keep adding and monitoring the p-values. As you add, monitor p-values, right? And you do that until the forward selection is added all the variables. It doesn't mean that the model now has all variables now. Backward selection part was taking out the ones that we do not need, right? So all variables in the model, we have sufficiently low p-value, and all variables outside the model that although we were adding, we were taking some out. And the ones that we took out, if we add them back to the model, they will have a large p-value that we do not need. They will have a p-value that we said this is our threshold, right? So those are the 3 methods The third one just being a combination of the two, right? So this backward selection, since backward selection looks at p-values, backward selection just looks at p-values, right? What it means is, for the p-values to be calculated, we need to have been able to fit a linear model, right? We need to have been able to fit a linear model. But for us to fit a linear model, it means we need our n to be greater than p, right? So what that basically means is backward selection cannot be used when your p is greater than n, because when your p is greater than n, you can't even fit a linear model. Since you can't even fit a linear model, you cannot even calculate the p-values for you to apply backward selection. So when your p is greater than n, you cannot use backward selection. But forward selection, you can use this always. This can be used always because it is concerned with calculating your RSS. So it really doesn't mind, and you're adding things as they go. It's perfect. You can use it always. Forward selection is one approach that is called, it is a greedy, it's said to be a greedy approach. It's a greedy approach because you might include variables early on. You know, when you're adding variables and calculating RSS, you might say, the one that gave me my smallest RSS now is X5, right? And then you add X1, you add X3, you add X10 and stuff as you are going, taking the ones that are giving you the smallest RSS per each step, right? But the risk that you run is you're going to include variables earlier on. Let's say your X5 that you added earlier on, that is going to be insignificant as interactions start happening as you add other values. You remember in our table previously, we had newspaper, right? Newspaper by itself, it was fine. So imagine we had started our forward selection by adding newspaper. It was fine. And then we add radio, cool. But then when we add TV, the third one, if you remember in our table, the newspaper stopped being useful. It stopped being useful. The p-value it shot up. It stopped being useful when the three were there and interactions started playing a part, right? But then with forward selection, there's no way of removing that newspaper that we already had because we're just adding. We are adding to the model. We're adding. It's greedy. It can take all the variables, even useless ones. So that's what sucks about forward selection. The mixed selection would be perfect in that case because mixed selection will say, you added newspaper before, but now, dude, at my third step when I added TV, newspaper stopped having a good p-value, so I'm taking it out. So mixed selection will take care of such a situation. Cool. That is the end of the video right here, right? We are going to go into the third question. The third question, which is assessing model fit, like just the model fit part, right? Now that we have selected the variables that we want, that are important, how do we assess that our model that we created there with these variables is accurate, or the model fit? That is going to be question number 3. And we're going to move on to the last, and then after that we'll move on to the last question number 4. So cool. Stay tuned for question number 3.